Or a 0. I guess a 0. That's right. Yeah, it could be all 0. Or at 0. So there's lots of non-endpoints. It's uncountable. Just use the same diagonalization argument. So there are way more points in here than you might imagine, right? There's lots of inaccessible points. They're points you can't reach, right? Okay, by being at endpoints. What else can you see? Does it have any interior points? No. What would it mean to be an interior point? Well, you can convince yourself that no matter if there were an interval around it, that around a point in this set, then some of those points would have to have 1s in their ternary expansion. Okay? Every point is a limit point. Why? Well, isn't it the case that no matter what number you give me, I can write this as a limit of a bunch of numbers that only have 0s or 2s in their expansion? Wouldn't you agree that this, for instance, is the limit of 0.0, 0.02, 0.020, 0.0202, ... Yes, every point is a limit point. Okay? So it's very, very interesting set. Question. So saw a question here. Bonnie. Oh, because K0 is the set of all numbers which have a ternary expansion in the 0th place, where A0 is either 0 or 2. K1 is the one where A minus 1 is either 0 or 2. K2 is the one where A minus 2 is either 0 or 2, etc. Then we're intersecting them all. Leon. No, because yeah, so I guess I'm defining all these to be always 0. Yeah, from A1 onward, I'll make them all 0. Okay. Yes. Not only is it a limit point of points in the real line, it's a limit point of points in C.
But what if it had a finite ternary expansion?
Oh, if it's finite, then that's an excellent question. That's an excellent question. So what if C every point is a limit point? Okay, now I've convinced you in this case. But what if it's finite ternary expansion? If it's finite, then it's gonna end in something, right? Like 0. Let's say 0, 2. There, that's finite, right? Well, I could write this as a limit of 0, 2, 2, 0, 2, 0, 2, 0, 2, 0, 0, 2, and send that last digit 2 off to the right. Okay. Happy with that? So Cantor sets are interesting. Yes, Emil. Why do we include the endpoints? If we don't, then this would be open. Well, I can't stop you from defining the Emil set to be a construction where you only use open intervals, but you'd have a harder time showing lots of things. So, for instance, of course, now that you have this insight, you can see it, but it's not obvious at first that the intersection is going to be non-empty, right? The intersection is not necessarily open either, right? Because the arbitrary intersection of open sets isn't necessarily open, right? I mean, you could. It's a great little fun project to figure out what you could show about such a set if you opened everything. Okay. Excellent question. Yes, Willie. Yes, but why would I not want to use the ones? Oh, right. Yeah, because I'm trying to show that it's a limit point of C. Every point in C is a limit point of C. Okay? Excellent question. Okay, yeah. So Cantor sets are really really great. Here's another property of Cantor sets, which is underappreciated. Underappreciated. Another property of Cantor sets that's really quite neat is that Cantor sets are there's lots of properties that are cool, but here's another one. Cantor sets are totally disconnected. Of course, now I have to define connected, so I'm going to do this. I'll define what this means soon. But the idea is that there's no connect. You give me 2 points, I can find a disconnection that'll separate these 2 points, and I'll have to make that notion precise very, very soon. Okay. What else? There was something else I wanted to say, and it just slipped my mind. What else is true about Cantor sets? It just completely vanished. Cantor sets. Oh yeah, this is cool. How long is the Cantor set? What do I mean by that? Well, what does it mean to define the length of a set for sets that are really strange like this one? One way you could define the length of a set is to ask, what are the lengths of possible intervals that cover this set? Okay? And then take the infimum of the sums of those lengths, right? You've already shown that closed intervals, you can only have countably many disjoint intervals, right? So you can talk about the sums of the lengths of closed intervals that cover a set, right? That has a certain length. And then do so for all such closed intervals that cover a particular set and take their infimum, and you could use that to define the length of a crazy set like this one. What's interesting about this Cantor set is, believe it or not, it has length 0. Okay? Its measures, the way we call it. We say C has measure 0. And one way to say that, I'll informally define it here. It can be covered for any epsilon, for any positive number epsilon, it can be covered with sets of size less than epsilon. For any epsilon, for all epsilon bigger than 0, C can be covered by intervals of total length less than epsilon. It's an amazing fact about the Cantor set. Uncountably many points, but length 0. Okay. Very, very cool. Good. So that's an introduction to Cantor sets. They pop up in all sorts of places, and don't be surprised if they pop up in our class as well. Okay, and on your homework, for instance. Okay, if you've looked at your homework, maybe this might give you a hint as to what to do with one of your homework problems. Okay, while I'm on the subject of the homework, I do want to mention one other thing about one of the